Yeah, way to set the bar low for me there. Yeah. So I have two lectures. The first one today, the next one on, I forget, Wednesday or Thursday. And they're about relationships between tensors and computational complexity. And so this lecture is going to be all about the computational complexity of tensors. And the next lecture is going to be mostly about what tensors can tell us about computational complexity. And I actually want to start, I wasn't planning on this, but it's sort of a good lead-in from Alexander's talk. So Alexander was saying, groups given by multiplication tables, it's sort of a totally unrealistic input for any reasonable size group. It's exponentially larger than when given by generators, and that's true. And if what you're interested in is doing computations on the groups, that's very true. But there's one problem, which I and several other people in the room are particularly interested in, where the state of the art is not significantly better in the worst case than if you were just given the whole multiplication table. And that is the group isomorphism problem. So the problem here is I give you two groups, and you want to know, are they isomorphic? And when I say I give you two groups, of course, it's given in a computer, so given how. Alexander gave a nice overview of the various ways groups can be given. I'm just going to divide this into sort of what I think of as two distinct problems, one of which is either you're given the full multiplication table, or you're given some form of succinct input, which I will just call generators. And I don't mean generators and relations, because in general that problem is undecidable, but I mean like I give you a set of permutations which generate the group, or I give you a set of matrices which generate the group, or maybe I give you a polycyclic presentation and a polycyclic set of generators, right? And in both of these cases, whether I give it to you as a table or as generators, the current best upper bound we know for the worst case of group isomorphism is if n is the order of the group, so that's like roughly the size of your table. I mean, it'd be n squared would be the size of your table. But if n is the order of your group, the best runtime we currently know is n to the O of log n. Okay. And there's a sort of trivial algorithm which does this, which is find a generating set of size log n, try all possible maps from that log n into the other group. There are n choose log n such maps, and for each one check if it's an isomorphism. Okay, this big O, you can do better than that, right? But it's actually pretty non-trivial to do better than that. The interesting thing is, like, if you have some groups in your hand, very frequently the algorithms that we use that are like implemented in GAP and Magma and things like that run much faster than this, but not always, right? And here, like I said, it doesn't matter whether I give it to you succinctly. If I give you, generating permutations, which are very small, and we have all of these super efficient algorithms for them, or I give you the whole multiplication table, right? Either way, the best algorithm we know is still n to the log n. Okay. And so one of the things that I have started trying to do with not just me, but with collaborators is break down this red-green blood feud of theory and practice of people that work on group isomorphism. So, you have to remember, okay, the motivation for worst case analysis is to get new ideas that will help us in practice, right? In fact, the whole reason that Jack Edmonds introduced the notion of polynomial time was just so that he could put a theorem behind his matching algorithm, right? He developed this matching algorithm. Prior to that, the best they knew was basically brute force. And he wanted to be able to prove that his algorithm was better, not just say, look, this is clearly better than brute force, right? And he even, if you go back and you look at Edmonds' paper, there's even this nice passage in there about like, don't take this definition too literally, basically. That it would be a shame if someone couldn't prove a polynomial time bound and said, therefore, this is totally inefficient. Right? And so you want to remember that like the theory can be a good guide, but it's not the end-all be-all, right? Similarly for practice, right? There are things we know how to do in practice much better than the current theory would suggest, but it's not the end-all be-all because those things don't always work, right? Okay, another reason that I and, let's say, people on the theory side are interested in group isomorphism where I give you the table is that group isomorphism, when I give you the table, reduces to graph isomorphism. Okay, and the current best runtime we have for graph isomorphism due to Babai a couple years ago is n to the log n squared. Right, so not so far from the current best that we know for group isomorphism. But then the interesting thing is that if I give it to you by generators, you get a reduction this way. Group isomorphism when given by generators in most models where I give you generators actually seems to be harder than graph isomorphism. Okay. So you have this sort of dual relationship where on the one hand, group isomorphism is kind of this bottleneck for making further improvement on graph isomorphism, right? But on the other hand, group isomorphism in the sort of realistic input models seems much harder than graph isomorphism. Okay. And I should say, in practice, this problem, practice, is essentially solved. So there are very good software packages out there, Naughty, Traces, I might be missing a couple, that work incredibly well for graphs up to like millions of vertices. It's very hard to stump them. We have one of the few people in the world, Taku Miyazaki, who actually stumped one of them and came up with examples that proved that this algorithm took exponential time. But it's very hard. And even Babai in his paper, at the end, he says, one of the things you should try and do is try and figure out, you know, what are the hard instances for these existing very good software packages. Whereas for groups, it's really not clear. Right? For many classes of groups we're interested in, it seems to be practically solved, but there are even sort of naturally arising families of groups that we don't really know how to solve well. Okay. And so the question is, well, how hard is this problem? Right? Is it equivalent to graph isomorphism? Right? Is it NP hard? Right? Oh, by the way, quick poll. Yeah, maybe since there are grad students in the audience, I will do this. All right, everyone close your eyes. This way no one is embarrassed. All right, raise your hand if you would like a quick review of P versus NP. Hands down, eyes open. Okay, great. All right. I will tell you, I won't say who, but I will say there were some students and some professors who raised their hand. Okay, so, right, but presumably you all know like NP hard means hard, right? Like we don't expect to be able to solve that in practice in many cases. Okay, and so our main tool for trying to understand this when we don't know how hard a problem is reductions. And actually, there was a question asked on, I forget what website, one Stack Overflow, something like what contributions has computer science given to mathematics? Because, you know, usually it goes the other way around. And there was a very nice list of these things, but one which stood out to me, I think it was Gil Kalai, who said that the notion of reduction came out of computer science, but it's really a very useful mathematical concept. And the idea, you know, we say this informally all the time, oh, I'm trying to solve problem A, I've learned some things where I've now reduced it to all I have to do is solve problem B. Right? But the idea is you can actually put a formal definition behind that, and there are various notions of reduction depending on what you're interested in. Let's just say for today we're interested in polynomial time. Again, polynomial is the theoretician's definition for efficient, but you have to recognize, you know, n to the 100 is not efficient, and there can be exponential algorithms that are efficient in practice, right? But let's just stick with polynomial time, so we have a formal definition. And I'm just going to do decision problems, so problems where the answer is yes or no, right? Very often you want more than that. Like if the two groups are isomorphic, you want the isomorphism. That's called a search problem. There's a question of if you can solve the decision problem, can you solve the search problem, right? That, like in graph isomorphism, the answer is yes. In group isomorphism, this is an open question. But let me just stick with decision problems. So We're going to limit our worldview to decision problems for the moment. So that just means the answer is yes or no. Right? I give you two groups. Are they isomorphic? Yes or no? Right? Okay. So a polynomial time. Oh, and by the way, I should say, this is how I lecture in class because I like the freedom. I'm not like tied to PowerPoint, but I will scan these in, and so you'll have copies of them. Yeah. Okay. So let's see. A polytime. There are lots of other adjectives, good adjectives, that I could apply to this notion of reduction, but just for today, for simplicity, I'm just going to call this a polytime reduction. From A to B is a polytime function, f, such that on any input x, a of x says yes, if and only if b of f of x says yes. Right. So f here is our reduction. The idea is you want to know the answer to problem A on instance x. You apply f to it, which is efficiently computable. You ask b, what's the answer to this? And then that's the answer to your original problem. Right. We use the notation, as I did up here. In this case, we say a less than or equal to, and in this case, you put a little p here for the polytime, and technically this kind of reduction, there's an m, but I don't want to talk about what the m is. Right, and the idea here is when you have this kind of reduction, what this tells you is up to polynomial time, A is at most as hard as B, right? Hence the less than or equal, right? Okay, and right, one of the advantages of these reductions is that even for problems where you don't know, the best algorithm, or maybe even for problems where you don't know any algorithm, right? There are problems where we still don't know whether or not they're decidable. You can relate those problems to one another by reduction. And one of the successes of computer science and this notion of reduction has been that there are these thousands of problems that are out there, and at first glance they all seem like different problems, but then they group into very few equivalence classes under this notion of reduction. And so instead of suddenly having to solve thousands of problems, you only have to know the complexity of a few problems. Okay. Right. Let me see here. Oh, right. So in our case, because we're going to be talking about algebraic objects, like, and I promise I'll get back to P versus NP in a minute. Because we're talking about algebraic objects, you might want more from your reduction, right? This still allows sort of an arbitrary algorithm, an arbitrary Turing machine. If our objects, for example, are, let's say, tensors over a vector space, right? Or I should say maybe tensors in a tensor space over a field, then maybe, we want it to preserve some of that structure, right? And surprisingly, for almost all reductions that are known, you can actually ask for it to preserve quite a lot of structure. And so the other thing that is common to ask for is what's called a projection reduction. This was originally due to Valiant in, I think it's 79. So a projection reduction, it's still a reduction like this. It could be polynomial time or not, right? We're going to want polynomial time projection reductions. And it has the property that, okay, we're now dealing in tensor spaces, so our things, if we choose a basis, our things have coordinates, right? And so you can ask, well, what is the output coordinate? What's the ith coordinate of f of x as a function of the coordinates of x? And in a projection reduction, the definition is that the ith coordinate of f of x should either be some coordinate of x, xj, or a constant. It doesn't have to be the same constant for all of them. Maybe I should put like c sub I, right? But it's literally just like I took one of my original variables, and it could be repeated, right? I could have many, that same variable xj could appear in many places in the output, or I put constants. Okay. And this, as you might imagine, this preserves sort of lots of structure, right? In particular, like, okay, we haven't forgotten the fact that we're working over a field, for example, right? We're not saying, oh, I'm breaking my field elements up into bits and I'm doing some funny Turing machine tricks to it, right? Okay, so all of the reductions that I'm going to talk about today are going to be polynomial time projection reductions, and they have a bunch of other nice properties that I won't get time to talk about. But yeah, we'll start with that. And you can make nice statements like these up here, right? So I don't know the complexity of any of these problems, but I can say, because I have proven reductions here, that graph isomorphism is at least as hard as group isomorphism up to polynomials when groups are given by tables, and when groups are given by generators, that's at least as hard as graph isomorphism. And it's natural to ask, well, are there reductions the other ways? Maybe all three of these problems are equivalent under polytime reductions. Let me just say this. So there is no reduction this way. No, I'm just going to write it. AC0 reduction this way. AC0 is a very small subclass of polynomial time. And this was a result of Chattopadhyay, Turan, and Wagner, I want to say in like 2008-ish, around there, sometime in the early 2000s. And so, okay, it doesn't actually rule out there being a polynomial time reduction in this direction. In fact, it's possible that all of these things are in polynomial time, in which case they're all sort of trivially polynomial time equivalent, right? But it's suggestive, right? It says there's not going to be a really simple reduction, right? And many of the reductions we know are in fact AC0 reductions. Okay, and here we don't really have any such evidence, although I'm going to give you at least some weak evidence today. Okay. All right, so that was sort of motivation. Oh, right, and then to bring it back to tensors, for a variety of reasons, it is fairly widely believed that the hardest cases of group isomorphism are groups with the following property. Exponent p, which means every element, the pth power of every element is 1, where p is a prime, and what's called nilpotent of class 2, which means that G mod its center is abelian. So the center is the set of elements which commute with everything in the group. If you mod out by those, what you're left with is a group where everything commutes with everything. Okay.
Do you permit the addition of 4 as an exponent?
I would, yes, I should have said for odd p this, or for p equals 4. Well, the issue is that groups of exponent 2 are all abelian. So 4 is like the first power of 2 where it's not abelian, where it's not forced to be abelian. And then if you take 4 here instead of p, or if you take p to be the prime 4, then yeah, those are also considered some of the hardest cases. Okay, and there's a standard correspondence which I won't go into because I think maybe Pete is going to touch on this a little bit, called Bayes' correspondence, which says that this problem, group isomorphism for these groups, is equivalent, again, Bayes didn't say it this way, but one consequence of Bayes' correspondence is equivalent up to polynomial time, to a certain problem on equivalence of tensors, which is, I'll tell you the name and then we'll see what it is in a few minutes. Alternating matrix space isometry, or following Wilson, pseudo-isometry. This is a name that James apparently made up that I didn't realize he made up. I thought pseudo-isometry was like a standard word because he presented it as just a standard word, and then I learned today at lunch that it was a word that actually he made up a few years ago. So yeah. And now it is a standard word, right? That's the... okay, but the real message here is this is a certain problem about equivalence of tensors up to change of basis. Okay. And so again, we get to this question of, well, how hard a problem is that? All right, so tensors And now we'll get a little bit to P versus NP. So, there's this analogy between tensors and matrices where you can think of matrices as two tensors, or I don't know, two valent tensors. Tensors, sometimes people say tensors with two legs. They call it the number of legs. Sometimes people say dimension, but we're not going to say that because that gets confusing. But matrices are two tensors. And so lots of problems on matrices you can try and generalize to tensors. So for example, the rank of a tensor. So let me just deal with three tensors now. So the rank of T, where this is a three tensor, meaning an element of some tensor space like this. This is the minimum R such that I can write T as a sum of, I goes from 1 to R, of, well, rank 1 tensors, but what are these? So this, by definition, is a rank 1 tensor, and this is the tensor. How should I write this? So this tensor here, let me call this R. Rijk, if you want it in coordinates, is, I have a clash of letters here. Let me RLJK, UIL, VIJ, WIK. So it's just the product. I took three vectors and you take sort of coordinate-wise product, right? And if I eliminated the third one here, right, this is the standard definition of a rank 1 matrix, right? So this definition generalizes the notion of rank for matrices. Rank for matrices, hopefully we all know, very easy to compute, right? Rank for three tensors already, so the next case after matrices, which are two tensors. So Johan Hastad in 91 proved computing tensor rank is NP hard. Okay, and now I will pause for a second to give a brief review of P versus NP. So the idea of NP was to capture this notion of brute force search. There were literally thousands of problems that people want to solve where there's an obvious brute force algorithm. So for example, is there a 3 coloring of this graph? Well, if the graph has n vertices, I can just try all 3 to the n possible colorings and see is any of them a legal coloring, meaning no two adjacent vertices have the same color, right? There's an obvious brute force algorithm. And there are lots and lots of problems which have this structure because, of course, it is the obvious brute force algorithm. And the question was, can you do any better? This was studied informally in Russia for a while, and actually research was sort of stunted because of this informality where a very famous Russian mathematician had basically claimed to prove that the answer was no. That there are these problems which can be solved by brute force where you can't do any better, right? And in today's language, we recognize he was essentially claiming that P was not equal to NP. And it wasn't until they actually wrote down the definition where they could say, no, like your informal argument does not actually resolve this problem, right? It only works for a limited class of algorithms. Right, and so this notion of NP was basically simultaneously developed by Cook in Canada and Levin in Russia on opposite sides of the Iron Curtain to capture this idea of problems which admit brute force search. And then once you have that, you can say, okay, now I have this very large class of problems, right? It's very interesting. There are lots of problems in here that people actually want to solve that admit this kind of algorithm. And the question is, can you always speed up this kind of algorithm? That's the P versus NP question. And NP hard, the definition here, is B is NP hard if for every problem in NP, it reduces to B. So NP hard problems are at least as hard as every problem that's solvable by brute force. Right? Now there are some caveats here, like for example, okay, does white have a winning move in n by n chess? Well, there's also an obvious brute force algorithm for that, right? Which is like try all possible games. But somehow that's a different kind of brute force than try all 3 to the n possible colorings. In particular, for each coloring, if I propose to you a coloring, you can tell very quickly, is this a valid coloring, right? You just look at all the edges and you see, do any edges have the same colored endpoints? Whereas for chess, if I run my brute force algorithm and I claim to you, right, for 3-coloring, if I run my brute force algorithm and I claim to you, yes, this graph is 3-coloring, I can very easily prove it to you, right? I show you the 3-coloring and you check in like linear time that it's a 3-coloring. Right? For chess, if I run my brute force algorithm and I claim to you, yes, white, for any n, white has a winning move, or whatever, for my particular n, whatever, n equals 100, white to play first has a winning strategy in 100 by 100 chess. Right? How do I prove that to you? I don't know, right? And neither does anyone else, as far as I know. This question is called NP versus P space. So NP is about this kind of brute force where for each proposed solution, you can check quickly. Is it a valid solution? But then beyond that, it's just brute force. Right? So NP hard means anything which can be solved by this kind of brute force. Well, your problem, in this case computing tensor rank, is at least as hard as all of those. Right? It's some sort of universality statement. Okay, so this was sort of bad news, right? This means you don't expect, in the current state of the art, you don't expect to get anything better than an exponential time algorithm. Even in the long run, if you believe P is not equal to NP, you don't expect to be able to do much better than that. Maybe in some cases you can have heuristics which work well, right? Which again, like in practice, there are many NP hard problems that on the instances people actually want to solve, we can solve them, right? But those algorithms we know don't work in polynomial time in general. Okay, so all right, computing matrix rank easy, computing tensor rank seems to be very hard. Right? So that was bad news. And then you might ask, well, there are lots of other things you could ask about tensors, right? You could ask about, eigenvectors, eigenmatrices, eigenvalues, sort of the entire, take any textbook on linear algebra and just try and generalize everything from matrices to tensors. And for a long time, people didn't know what the complexity of that was. And then there was this beautiful paper by Hillar and Lim called Most Tensor Problems Are NP Hard. And I'm not going to walk through all of these problems, but you can see they have like this huge list of problems on tensors. And, except for they have a few conjectures here about some of, a few problems that are left over, they prove that all of them are NP hard. Right? Most of these results, I should say, you'll see they're like over the reals or the complex numbers. And even some of them which don't say this, right? Like this doesn't say over R, but this is non-negative definiteness. It's clearly over R, right? So most of this paper is focused on R and C. One of the things coming from the group world that you're very interested in is like over the integers mod P, right? And so some of these problems aren't even defined if you're not over R, but for the ones that are, like if you ask for it over, Z mod PZ, some of them I think are known and some are still open, how hard is this? But based on this and the fact that tensor rank over any field was NP hard, we sort of expect them all to be NP hard. So like even getting the most basic information about a tensor seems to be very hard. And then remember that the problem that we were interested in is not particularly basic, right? It's I give you two tensors, is there some change of basis which takes one to the other? Right, yeah.
Sorry, maybe you mentioned this, but in that list that you had up there, you were saying before that sometimes in the cases people care about, they actually, it's actually not so bad. Are there any examples there where that's the case, or most of them seem to be even in practice?
Right, so the question was, I said for some NP hard problems, or really NP, let me say, yeah, fine, yeah, NP hard problems, even in practice for the instances people care about, we can solve them even though we know we can't do it in general. Is that the case for any of these problems? And the current state of the art seems to be kind of no. That like even for most of these problems, at very low dimensions, they become very hard very quickly, right? Some of these problems, not these problems, but closely related problems, you can very quickly get into like Grosvenor bases, which require like exponential space even, let alone exponential time. And yeah, these problems seem to be hard. Actually, a project that I have a student working on, Arthur, who's here with us, is trying to apply SAT solvers to tensor isomorphism. To see, SAT solvers are one of the notable successes in this area where they work very well in practice. Although you can, even for like SAT instances with millions of variables, but you can fool them with a random instance with a few hundred variables, right? And like you can produce random instances like that where still literally no one knows whether that instance is satisfiable or not because it's so large you can't do it by hand. It was produced randomly, we don't know, and no algorithm has been able to crack it, right? Right, so one question that we had was, well, what if you take those SAT solvers, which seem to work well in practice, does that make tensor isomorphism work well in practice, right? So we'll see. He literally just started like 1 week ago, yeah, so, yeah. Yeah, yeah, come on. Right, but basically all problems on tensors at the moment seem to be hard even in practice. Yeah. I should say, if the answer you're interested in is only approximate, then things become easier, right? Like large swaths of machine learning are some form of approximating something about tensors, and then you can do stuff. And actually Chris Moore, who couldn't be here today but is coming tomorrow and is giving a couple tutorials, will talk about tensors in machine learning. Yeah, great question. Okay, so let's see, good. Right, most problems are NP-hard. All right, so now I want to come to sort of the meat of my talk, which is, well, what are these tensor isomorphism problems that I've actually been hand-waving about, and how hard are they? Right. So some people call this tensor equivalence. Yoming Chow and I, who are writing a paper on this, which we were supposed to put on the archive last week, but then we proved some new things, so hopefully be on the archive this week. I think that it's better for a variety of reasons to call it tensor isomorphism rather than equivalence. It connects it with a whole family of other isomorphism problems. Equivalence asks, well, equivalence under what, right? Whereas tensor isomorphism, well, your tensor lives in a tensor space, as I think maybe James will tell us in his next talk, there are categories in these tensor spaces, and they all have notions of isomorphism, and so this is, isomorphism in at least one of those categories. All of them, yeah. Sure, yeah, right. The question is whether I'm going to talk about all of them. Yeah, which actually I guess sort of I will, but not in full detail. Okay, so let me just do sort of the plain vanilla case, which is I'm going to say I have two tensors, TA and TB, in the same tensor space. And on this tensor space, there is a natural action of this group. So I can do linear change of basis in the vector space U, which if you like, you can think of as the rows, linear change of basis in the vector space V, which is like the columns, and linear change of basis in the vector space W, which is the third direction, which we do not yet have a common name for. Some people call them the depths. So you have rows, columns, and depths. I've also heard them called the tubes, because it's like a tube going, yeah. So I don't know what to call them, but it's the third direction. Okay, and you can ask, given two tensors, can I change basis in the rows, columns, and depths, let's just call them for now, to make one equal to the other, right? So if instead of, just by analogy, right, if instead of three tensors I was doing two tensors, which would be matrices, so let's say I have M1, M2 in U tensor V, so I just have two, right? Well, the action here is now, so this question is now, does there exist invertible x and y such that x M1, let me say y inverse equals M2. Right? And here I'm allowing row operations and column operations. And we know for matrices, if you have row operations and column operations and you're over a field, you can always put this into a normal form. Normal form, which looks like an identity matrix whose size is the rank of your original matrix and then zeros. So over matrices, this problem is trivial, right? But as we might expect, given the story I've been telling you, over tensors, this problem seems to be much harder, right? At the very least, one version of this problem is group isomorphism when groups are given by generators, and you're in this hard family of groups, right? P groups of class 2 and exponent P. And so that's like at least as hard as graph isomorphism, so immediately you get some hint that like, yes, this does appear to be much harder than the matrix case. Right? Right, now there's a whole slew of problems. So in matrices, right, we don't just have this problem. I think James had this in his slides, right? This is left and right. You could also ask, you know, so that's one problem. There's another problem which is, well, what about if I do x m1 x inverse? So conjugating by a single invertible matrix. Right, and here we know you also have you have a normal form, Jordan normal form. Or you could ask about x m1 x transpose, where here I'm treating m as a bilinear form, right? Which means it's like a map. It takes in two vectors u and v, and those go to u m v transpose. And I'm considering change of basis, where these two are in the same vector space. So I apply x to both of them, right? So this is like ux m vx transpose, right? So I've changed basis in my vector space, but I can also view that as changing the matrix. So these three are different things, and it's nice to have notation where we can very succinctly express this. And so this, I guess, this notation I think is somewhat orthogonal to the notation that James was introducing, in the sense that you could use both of them, and I think they gel together well, but like neither one requires the other as a prerequisite. So I've already started using it a little bit. The idea is each vector space gets a name, in this case UVW, right? And if the same vector space appears twice, well, it's the same group, you know, GLU. It's not two copies of GLU, it'll just be that one copy of GLU acting on it. So this problem here I would denote by U tensor U star, where U star is the dual vector space, okay? And this problem here I would denote by U tensor U. So this was U tensor V, right, left and right. This is U tensor U. The transpose comes, this is sort of an artifact of our notation for matrices, because you're acting on columns, and columns we write this way, and rows we write this way. But if you look at what the action is in this notation, it's really, you know, GU tensor GV, right? So G acting on U tensor V is like this. Oops. That happens in my class too. Okay, and that's why there's no special decoration. It's really the same group acting in the same way on these things, but when we write it as matrices, you have inverted half of your or not inverted, but transposed half of your coordinates so that they look like columns, right? Okay, so in the same way, you could talk about tensors. So we have U tensor V tensor W. This is sort of the generic tensor isomorphism where all three factors are different, right? You can also talk about, you can just add another vector space to all of these. U tensor U star tensor W, U tensor U tensor W. And so these three are sort of straight up generalizations of the matrix case. And what are they? Well, as James mentioned briefly, I can think of this if W is, I'm running out of letters, let's just say m-dimensional. I can think of a tensor T in here as an m-dimensional space of matrices. Okay, and the way I do that, let me just rewrite. Oh. This is one of the joys of paper, is that like I don't have to worry about, oh, was that on the previous slide? Like, no, it's at the bottom of the previous slide. Like, that's okay. Right, and the way I do that is, you can think of it in a variety of ways, but let me just write it like this. So I have my 3 tensor, and if you choose coordinates, you can write down a box, just like with matrices. You know, you have an element of a matrix space, you choose coordinates, you write down a matrix, which is a box. And I'm just going to label these, so this will be my U axis, this will be my U star axis, and this will be my W axis. And then I can just look at the slices this way. right? Each slice here, so there are m of these because we said W was m-dimensional. Each slice here is a dim U by dim U matrix, right? And why is it sort of okay to think of this? So the idea is I have my tensor T here, and I want to think about this as the span of these slices, and let me give these slices names. So let me call these slices, I don't know, T1, T2, T sub m. So I can think of this as the span of Ti for I in m. Okay. Why is this sort of a, like, sure, yeah, you can do that because it's a box of numbers and you can do whatever you want with a box of numbers, right? But why is this sort of a reasonable thing to do? Well, because the isomorphism problem I'm talking about here is I get to change basis in W. That's part of it. Right? And changing basis in W corresponds to taking linear combinations of these slices, but it preserves their span. Right? So when I talk about this matrix space, right, it's a linear space of matrices, the action of W is sort of implicit. Right? The action of W is precisely the things which preserve this span. Right? And so now, if I give this matrix space a name, let's say curly T, and this is the disadvantage of not using slides, is that in slides I have like 7 different fonts I can use. Now, this problem, U tensor U star tensor W, is the question of I have 2 such matrix spaces, curly T1, curly T2, and the question is, does there exist an X in GL U such that X curly T1 X inverse equals curly T, not a psi, curly T2, where this is just the span of the set of X Ti X inverse. And now the beauty of this is like we're all used to thinking about matrices, right? And now I'm just conjugating matrices, so I know some things like, well, when I conjugate matrices, their eigenvalues are preserved, for example. Right? Now I have a linear space of matrices, so you have to ask not just what are the eigenvalues, but like how do the eigenvalues vary across this space? But now you can think about eigenvalues, right? And like computing the eigenvalues of any one element here, any one matrix is still easy, right? Whereas there is a notion of eigenvalue for tensor. Computing eigenvalues for tensors is NP hard, right? It's not this, obviously. Right? This is a different notion, but the point is this could still be a useful notion, and you could imagine for isomorphism, like what eigenvalues appear here, or for example, what ranks appear here, could be a useful invariant for isomorphism, right? And I think Taku is going to talk a little bit tomorrow about the complexity of telling what ranks are in a given matrix space. Okay. Right. Okay, so we have some problems, right? We have U, V, W, U, U star W, and U, U, W. And now we get new problems because I can also look at U, 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 right? And I could also look at U, U, U star. Okay, this, just like U tensor U was bilinear forms, U tensor U is just trilinear forms. Okay, and U tensor U star, well, I'd really like to sort of dualize this and think of this as U star tensor U. That doesn't really change anything because that's like, instead of using X, I used X inverse, right? But like which coordinates it appeared in versus which coordinates it appeared inverse in was the same. Right? So this I claim is the notion of an algebra. Right? If I think of U as A, well, this is a map from A tensor A to A. So it's a bilinear map from A to itself. Right? It's not associative. It doesn't have a unit. It's not commutative. It's a general algebra. Right? It could be, you could have things in here which are associative. You do. Right? And if you do, I claim that, you know, this isomorphism problem for those tensors is just R2 algebras isomorphic. Okay. So great. For 3 tensors, just 3 tensors, right? We haven't done like D tensors yet. I now have, instead of just 3 problems like I had for matrices, where I know the answer to all 3 problems, I now have 5 problems, and I don't know the answer to any of them, right? Okay. And so the first thing that happened was I asked this question at a workshop in 2015, which was sort of one of the predecessors of this workshop. I'm just going to say V because I don't know how to pronounce his first name. V. Futorny and Vladimir Sergeychuk. They really did most of the work, but I'm on this paper as well. Proved that all of these problems reduce to 3 tensor isomorphism. They reduce to U tensor V tensor W. And in fact, more than that. So all reduce to U tensor V tensor W. Right. You know, they did other things like, oh, what if you want to partition your space U as a direct sum of subspaces and you want to preserve that partition? Okay, that also reduces to this. What if instead of equating one tensor and another, I want to equate 6 tensors with 6 3 tensors with 6 3 tensors? Okay, that also reduces to this, right? There's a whole bunch of things. Okay, so that tells us sort of one direction, right? U tensor V tensor W is sort of universal for these 3 tensor problems. But what about the others? Are they universal? Are they maybe easier, right? And so in this paper with Yoming Chow, which was supposed to be on the archive last week and should be on the archive this week, we actually prove these are all equivalent. And so let's see, this paper with Futorny and Sergeychuk, that appeared earlier this year, and this is like the future. You're welcome to the future. Right, so these results, this is like the first announcement of these results. These have not been announced previously. So these are all equivalent, and actually part of the reason for the delay was that we just proved last week that this is also true for D tensors. So also, U1 tensor UD reduces to U tensor V tensor W. So D tensor equivalence is equivalent to 3 tensor equivalence. Okay, and let's see, in my last, when did we started 10 after? So I have like 13 minutes left. Right, okay, so I want to show you a big picture of like all the reductions, and then in my last few minutes I want to give you some sense of like how do you prove this kind of reduction, right? So let me come back to the laptop here. Right, so, all right. I'm very proud of my tech skills in this picture. This was made entirely in native tech. So here you see graph isomorphism. Here's group isomorphism in the table model. Here's the class of groups that we were talking about, right, which seem to be no easier. There are lots of things in this picture, but I just want to draw your attention to a few. So over here is factoring integers, right? That's a problem that we typically think of as hard because lots of security of crypto systems rests on that. That reduces to various other problems here. This problem is in the box, which means it is equivalent to tensor isomorphism. So tensor isomorphism over the rationals is at least as hard as factoring integers. Okay, so like we already knew, right, it was at least as hard as graph isomorphism. It's also at least as hard as factoring, so that's some evidence. Like I said, maybe factoring is also in P, but okay. This reduction was originally due to Laios Ronyai in '88, but the equivalence of this with all these other things is in our paper. Let's see, what else did I want to draw your attention to here? Oh, right, so in terms of computational difficulty, this problem we can solve in n to the log n time, group isomorphism when I give you the table. Graph iso we can do, and string iso we can do in n to the log squared n time. Right. Code equivalence, which I'll come back to in a second because that's the example I'm going to show you, we know how to do in like 2 to the n time, but not really better than that, but in many cases can still be solved efficiently in practice.
What's AS?
AS, oh, in the citations? Oh, the question is what's AS in the citation? That's Agrawal-Saxena, 05, yeah. Yeah, see the paper for all the citations. The main ones here are Agrawal-Saxena, my paper with Futorny and Sergeychuk, Baer, this is Brooksbank and Wilson, this is a paper with Babai, Paolo Codinotti, me, and Yoming Chow, Zemlyachenko, and some other people whose names I can't pronounce. Yeah. Right, but the point is there's this whole slew of problems, right? So this is like isomorphism of associative algebras with unit. That isomorphism problem is equivalent to isomorphism of 3 tensors. This problem here is I give you some matrices which form a commutative Lie algebra, meaning they all commute. I give you 2 such things and I ask you, are they conjugate? Not just abstractly isomorphic, because as Lie algebras with 0 bracket, it's not hard to tell that. But are they conjugate? That problem is equivalent to isomorphism of 3 tensors. Okay. All right, so we have this nice big diagram, right? We know how to solve these things in 2 to the n time, but not much better, but they can still be solved in practice. And up here, we know how to solve things in like q to the n squared time and not even in practice, right? And q to the n squared is basically enumerate gln over fq, all of it, and just see, literally check all possible changes of basis. Yeah, Jamie? The box in the top left, yes, this star here is because some of these reductions only work over certain fields. That's the, in particular, I think it's like fields in which every element has a dth root. Yeah. Okay. All right, so now in my last few minutes, I want to give you some sense of how some of these reductions work and what are some concepts that go into them that might be useful for other things. So let me go back to my paper here. All right. And to do this, sure. Okay. So the motivation for at least one of these reductions was, and there are several different techniques, but I'm going to show you sort of the main new one, comes from graph isomorphism. So in graph isomorphism, people often also talk about colored graph isomorphism, where the vertices have colors. And you need your isomorphism to send red vertices to red vertices and blue vertices to blue vertices and so on. And you very quickly realize that like colored graph isomorphism and graph isomorphism are actually the same. And the way you do that is, suppose I have a graph, it has some stuff, and I want to color, let's say, just this vertex for the moment. Let's say I want to color it a new color, blue, because that's the pen I have. Well, I can turn that into a graph where this part is the same, and then to this vertex, I'm just going to attach a whole bunch more vertices of degree 1, where the number of vertices here is going to be n plus 1, so it's more than the number of vertices of my original graph. Right? Because it's more than the number of vertices in my original graph, this is the unique vertex in this graph, which has n plus 1 things of degree 1 hanging off of it. And so now if I had 2 graphs like this and I colored one vertex red in each of them and I did this construction to each, well, the uncolored graphs would be isomorphic in the usual sense, if and only if the colored graphs would be isomorphic. Okay. So the idea was, can we generalize this notion to the multilinear algebra setting? And although we didn't come up with this way, I think it's sort of a nice motivation. Here, the key thing we were leveraging was that vertices have degree. Right? We just made this vertex have degree guaranteed to be higher than any other vertex. Right? So the question is, okay, in linear algebra, you don't have a finite set necessarily if you're over an infinite field. So what should be, I give you a tensor, and I tell you a vector, what should be its degree? Right? So let's say I have a tensor, TA, in U, V, W. Okay. So what I can do, and let me just draw my box picture here so that I have things right. This is L, N, M, N. So I'm going to have N here, maybe L here, M here. Okay. So what I'm going to do is I'm going to look at slices now in this direction. These I will call lateral slices. And the idea, so this is a matrix, so if this is L, M, N, N, so this is like U, V, W. So the idea here is when I pick a slice this way, I fix an element of W, right? And I'm just looking at the U tensor V part. So I'm looking at a matrix in U tensor V. So the ith lateral slice is in U tensor V, and it's L by M. And what I'm going to say is for any V in, or let me say for all W in W, I'm going to define the degree relative to this particular tensor of W to be, I take a linear combination of these lateral slices, so my vector W is telling me which slices to add up in what proportions. So sum Wi, Li. And then I'm just going to take the rank of that. Right. And in graphs, this sort of makes sense. Like in the adjacency matrix of a graph, the degree is the number of ones appearing in a row. Well, now we have, our slice is not a row, it's a matrix now. So the number of ones appearing is a little bit too, not linear algebraic enough. It's sort of too combinatorial, but rank is a perfectly good linear algebra thing. And so the question is, say I want to do a reduction from the following problem, which is called monomial code equivalence. So this problem is I have two matrices A and B, which are N by M. And the action I'm going to have is, the question is there an invertible X and a monomial matrix Y, which means this is a diagonal matrix times a permutation, such that X, A, Y equals B. So the idea here is, if you think of A this way, I'm allowed to permute the columns, and I'm allowed to rescale each column individually, and I'm allowed to take linear combinations of the rows. Right? So again, if you like, I can think of this as A is telling me a linear space of vectors, which is its row span, and I have two such linear spaces, and the question is, can you permute the coordinates and rescale each individual coordinate to get the two to be the same? Okay, and the claim is this reduces to three-tensor isomorphism. I won't have time to go through the whole proof, but I will have time to show you the construction. So the construction is we're going to use this idea of degree and the idea that, well, what do we want? In three-tensor isomorphism, you have linear change of basis in all three factors. We don't want that, right? We want linear change of basis in this factor. We want only monomial change of basis in this factor, which is like permutations and scaling. So how do we do that? Well, the idea is you make the columns which appear here be special among all possible linear combinations of columns, and we do that with rank. So we're going to build a three-tensor which looks like this. In the front slice, I'm going to put my matrix A. So this is like I'm now thinking of this as a 1 by n by m three-tensor. Okay. And then one step back from that, in the first row, I'm going to put a little 2 by 2 identity matrix. So I2. So the rank of that lateral slice is now 3. Right? Because I put a 2 by 2 identity matrix. It's in separate depths. Right? Okay. And then in the next slice, I'm going to do the same thing, but like totally independently. So this is in the next column over, right? So it's in the next column over, right? So that second lateral slice now also has rank 3. Okay, and I do this for all the slices. And now the key thing is, if I take a linear combination of these slices this way, I get at least 2 of these identity blocks. So any non-trivial linear combination of these slices has rank at least 5. Or let's say 4. 4 is enough, right? Whereas any of these actual slices has rank at most 3. So now in this tensor, any equivalence, because of this rank condition, has to preserve the lateral slices. It can permute them and it can rescale them, but it can't take arbitrary linear combinations. Right? So this is like individualizing my vertices. Okay, and now I'm out of time, but let me just say, okay, then you can work out, okay, if the two codes are equivalent, you can work out what is the linear transformation you do to these things, and it's like, well, you permute the lateral slices and you do the scaling. And then the bad thing is like these identity matrices got scaled, but in the third direction, you then rescale them back to be identity matrices. And then the converse I sort of almost proved to you already, which is if these two tensors are equivalent, then it has to be a monomial equivalence of these codes. So that's one of the basic tricks we use. Another, which is a funny trick, is you take one tensor and you put it sort of in the upper left block of another tensor and make the rest 0. That often works as a strategy for reduction. That trick is like, on the one hand, it's trivial. On the other hand, it first got used in representation theory by like Gelfand. So yeah, we were considering in our paper calling it like the Gelfand trick to make it seem less trivial because, you know, it goes back to this like very serious mathematician. But right, so there are a few strategies you can use. This is sort of the big new one. But this lets you reduce a lot of these problems to one another, and then, you know, you start piecing these things together. And actually, the interesting thing is we weren't actually sure of this at the beginning, that all of these things would be equivalent. We, at some point, like after a couple years of going back and forth, we thought like, oh, maybe there are actually a few different classes here, and like that's okay. It's sort of, you know, it's still an interesting complexity landscape. And then at some point we had, you know, some other idea for some of these other reductions, and we realized like, hey, wait a minute, we now have cycles everywhere in our reductions, and they're all equivalent. Yeah, so that brings us back to this thing of, you know, our original motivation. Where did that go? Group isomorphism, where the question was, how hard is group isomorphism given by generators? And for this class of groups, which we thought were the hardest anyways, well, we don't know the answer, but we now have sort of a coherent complexity landscape in which they sit, and, you know, it turns out to be equivalent to a lot of other problems that people have been trying to solve. So yeah, I will stop there, I think. Thanks.
You, at the very last page, you had the I2s, 2x2 identities. Maybe you said it and I missed it. What's so special about the 2?
Oh, right. So the question is, what's so special about the 2 in this reduction? The main special thing is that 2 plus 2 is bigger than 2 plus 1. Or in this case, 2 is bigger than 1. Right. Now, there are other reductions. So this is sort of one of the easy reductions where it's something, you know, monomial code equivalence we don't think is actually equivalent to the other problems. It just reduces to them. For some of the equivalences, the numbers matter more. Like you'll have some slices where you need it to be at least n, for example, just like in the graph case we had it at least n, but then it's like some slices where it's at least n, but all those slices have to have equal, and then you'll have another set of slices which also have to be at least n, but a different value, like, so it you know, yeah, you get sort of layers on layers of these reductions and they get more complicated. But in this case, it was just 2 is bigger than 1, yeah. Yeah.
Yes, so this is more like a meta question, but so when you formulate those isomorphism problems, so you have two objects, this one and one is isomorphic to another. So you're basically looking for permutation, right?
Or a change of basis.
Change of basis.
Yeah.
So I'm more comfortable with thinking of permutation. So let's just say it's a looking for permutation.
Okay.
And you're asking a question whether there's an element in So I guess my question is it useful or maybe not useful to formulate such question by including group or something that's acting on these objects as part of the.
The group would be, in this case, GLU cross GLE cross GLW.
Yeah.
Acting interpretations on the tensor product.
Yeah.
Right.
So my question is, but rather than including the whole, so this is like the entire group, right?
Oh, you mean like what if you had subgroups?
Yeah.
Ah, right. Okay. So the question is, what if instead of GLU cross GLV cross GLW acting on